Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. This is the second module. In the second modules, we are in the third lecture. In the second module, first two lectures, we have seen the working principles of capillary viscometer and possible sources of errors in capillary viscometers and correction methods. In this third lecture, we are going to see rotational viscometer. In rotational viscometers, we have different types of viscometers. Different types of geometries are possible actually. Concentric cylindrical geometries where either of the cylinders may be rotating or one of them may be rotating. Then we have a cone and plate viscometer. Then we have the parallel disc viscometers. So, we are going to discuss about three rheometers, their working principles here in this lecture. However, we are not going to derive any of these equations because of not getting away from the main part of the course on the transport phenomena, but not on the rheology. However, since we are discussing transport phenomena of non-Newtonian fluids, some information about the rheology of non-Newtonian fluids is required. So now let us start with the concentric cylinder viscometers. Concentric cylinder rheometer, first practical rotational rheometer was the concentric cylindrical rheometer proposed by the Guwahati in 1890. Today, most commercial instruments utilize similar design. Working equations relating shear stress to torque measurements, shear rate to the angular velocity and normal stress differences to radial pressure differences are developed in general. So that we get in general, like if you have when you take equations of motion in different coordinates, let us say r, theta, z components. So from each of the component you when you simplify according to the geometry and then constraints of the geometry, you will get three different relations. Each one will give a kind of information about the hydrostatic pressure, normal stress and shear stress. So however, we are not going to derive them in this particular course. Now what you do, consider a flow of a fluid confined between two concentric cylinders with inner cylinder rotating with rotational velocity omega I. Now this is the geometry here shown. There are two cylinders. This inner cylinder is there and there is a outer cylinder is there. So this inner cylinder is rotating at particular angular velocity omega I. The radius of inner cylinder is Ri, radius of outer cylinder is Ro. The height of the cylinder is L. The gap between these two cylinders, the concentric gap, that is Lb. Okay. So now in these conditions, in this geometry, we see what are the possible conditions that we can imply. Let us assume the steady laminar isothermal flow, since actually the gap depends on the gap. If you have a narrow gap, so steady laminar flow conditions would exist here. And then what we have, Vr, V theta and Vz components in cylindrical geometry, out of which only this V theta is existing because rotation is taking place in the angular direction, and because of that rotation only there is a deformation. So shearing is taking place in that direction, right. So what we understand, so from this geometrical thing, so that this Vr is not existing, Vz is also not existing, or even if they are existing, they are much smaller compared to the V theta, hence they can be neglected. And then in this geometry, assume there is no gravity and effects. Also because of the laminar conditions, motion is at the smaller rates, so one can assume the symmetry in the theta direction. Now what could be the boundary conditions here in these conditions? So here inner cylinder at r is equals to Ri, that is rotating with angular velocity omega I. So then velocity V theta would be omega I into Ri, whereas the outer cylinder at r is equals to r naught, it is stationary. The outer cylinder is stationary, so V theta is 0. However, in some geometry it is also possible that both of the cylinders may be rotating at different rotational velocities. So in such case, at outer cylinder V theta would be omega naught r naught at r is equals to r naught. Now let us do the force balance on the inner cylinder surface, because inner cylinder is rotating. So because of rotation, whatever the torque force is there, that should be balanced by the shearing force. So for that case, we have mi by Ri is equals to tau r theta 2 pi Ri L. So tau r theta is function of Ri. Now 2 pi RIL is the surface area of the inner cylinder. So, from here we get tau r theta function at R is equals to R I is equals to m I by 2 pi R I square L. M I is nothing but the torque. Let us say if the outer cylinder is also rotating, then similarly we get tau r theta at R is equals to R naught is equals to m naught by 2 pi R naught square L. Now, this is about the shear stress information. So, now we understand from here the shear stress that fluid for which we wanted to know the rheology, which is confined between concentric cylinders. So, inner cylinder is rotating. So, in such case the shear stress is related to the torque Mi if inner cylinder is rotating, torque Mo if outer cylinder is rotating. So, shear stress expressions we have already got. Now, what about the shear rate expressions? Shear rate expression, it will again depend on the ratio between the radii of inner and outer cylinders, that is Ri by R naught. If the gap is very narrow, then there will be some expression for the shear rate. If the gap is very large, that Ri by R naught, if very small value, then that means gap is very large, then there will be some different shear rate. Then in other case, like fairly narrow gap is there, neither very narrow gap nor very large gap, then there will be some other relation for shear rate. Now, we see those expressions for shear rate, and as per the problem we have to use the corresponding expression for the shear rates. So, shear strain and shear rate, let us take very narrow gaps range, as I said K. Now, let us indicate that Ri by R naught ratio as K if it is greater than 0.99, that means almost both the cylinders are touching to each other, that close, they are very narrow. So, in such narrow gaps one can simply forget about the curvature effect, and then shear strain can be obtained by the delta x by delta R. So, delta x is the displacement. So, we have to convert into the angular displacement. So, that theta multiplied by r. Theta at what location? Though the displacement or the gap is very small, at what location are you measuring? So, let us assume at midpoint between the at midpoint of the concentric area, whatever is there. So, that is the at average distance of Ri and R naught. You are measuring this angular displacement. So, gamma is equals to R. Shear strain, not the shear rate, shear strain is theta R by R naught minus Ri is nothing but the gap between the two cylinders, concentric gap region. Similarly, under such small narrow gap conditions, the velocity gradient would also be constant across that narrow gap. So, then one can have the shear rate expression gamma dot at Ri, we wanted to measure at Ri is equals to del V by del R. So, sigma I divided by R naught minus Ri, that whatever the distance is there, this one can take the average value, this R bar value. So, that is R naught plus Ri by 2. So, now what happens for the case of narrow gap range, we have the expression for the shear rate. So, using the shear rate expression and previously developed shear stress expression, one can know the rheology of the fluid by their angular velocity and then torque. So, let us say if we have a large gap, because in general it is not possible to have such narrow gaps like Ri by R naught greater than 0.99 is not possible. So, but often we have K less than 0.99. So, in that case we need to carefully develop the relations. So, how to develop the shear rate expression? From rate of deformation tensor, we have a gamma dot is equals to mod 2 tau r theta. So, this 2 tau r theta that is available in the book. So, that this nothing but dou v theta by dou r minus v theta by r. There is other Vr terms would also be there, but Vr is anyway 0. So, then we are not writing here. So, this dou v theta by dou r minus v theta by r, we can write it as r dou by dou r v theta by r. So, v theta by r is nothing but the angular velocity. So, then we have shear rate for this case as r dou omega by dou r. So, after doing some certain simplifications etc., we get the shear rate expression for large gaps in the sense when K is less than 0.1. So, that is a huge very large gap. So, under that conditions, when we do some simplifications of the expression from the equations of motions, then we get a particular relation, right. When we relate them to the angular velocity, then we get gamma dot r I at outer cylinder is approximately equals to 2 omega I d ln omega I by d ln tau r I, right. So, this equation number 10 we can get by substituting tau r theta is equals to m I by 2 pi r I square L in this equation number 9. So, then we get equation number 10. So, now here also we have an expression for the shear rate. Previous expression is for the previous expression of shear rate is for the narrow gap concentric cylinders geometry. For large gap concentric cylinders geometry, this expression of the shear rate one has to use. But in general, neither large gap nor the small gaps are used, but fairly narrow gap concentric cylindrical geometries are in generally used. So, in such case what we have? We have an expression for shear rate given by this equation gamma dot function of tau r I is equals to omega I by minus ln k multiplied by 1 minus ln k by n plus ln k by n whole power 2 by 3 minus ln k by n whole power 4 by 45, like this Maclaurin series we have. Whereas, here in this Maclaurin series whatever the n is nothing but the slope of mi log plot of mi versus omega I, or ln m I versus ln gamma I plot. If you plot in such conditions, it is most probably that we may get a straight line and then slope is given by n. This is also known as the power law index. Now, to be precisely like in the case for like in this Maclaurin series, which terms are negligible, which terms should be considered, that depends on the value of minus ln k by n. If minus ln k by n value is less than 0.2, then first two terms give error less than 1%. So, one can avoid the higher terms, third term onwards one can avoid. But if this minus ln k by n value between 0.2 to 1, then third term should also be added. But for the case of k where it is greater than 0.5, if n is constant over the region tau r I to tau r naught, then one can have the power law case, and then shear rate is given by this expression gamma dot r I is equals to 2 omega I divided by n into 1 minus k power 2 by n. If let us say outer cylinder is rotating, then the corresponding shear rate expression in this case will be gamma dot r naught is equals to minus 2 omega I by n into 1 minus k power minus 2 by n. So, in such case number of concentric cylinder instruments rotate, outer cylinder rotates at omega naught and maybe inner cylinder is fixed. So, in such case what one can do, one can replace omega I by omega naught and then simply move forward to the calculations. Now, what we do, we take an example problem and then see how to develop the rheological curves from the rotational velocity versus torque information that we get from the experimental setup. So, here the following steady shear data for salad dressing has been obtained at 295 K using a concentric cylinder viscometer, for which the radius of inner cylinder is 20.04 mm, whereas the radius of outer cylinder is 73 mm. That means they are not in the narrow gap because the difference is too much. So, we have to find out how much is the K, and then accordingly we have to use the equations, and then height of the cylinder is 60 mm. So, the rotational velocity of the inner cylinder is given omega in radians per second, and then corresponding torque generated is given in Newton meter. So, what we do? We have to first find out what is the ratio R I by R naught, which is K. So, accordingly from this ratio we have to use appropriate gamma dot expression, gamma dot R I expression we have to use. Otherwise, tau R I expression is anyway same for all case, that is 2 mi by 2 pi R I square L. So, now we do sample calculation for one point and then others similarly can be done. So, R I by R naught, it is here is 20.04 divided by 73, it is 0.275. So, now it is neither larger than 0.99 and it is not less than 0.1 or 0.01. So, that this is neither a narrow gap range, this is not a large gap range, but it is in between range. So, we have to use this gamma dot I information. Gamma dot Ri is equals to 2 omega dln omega divided by dln tau Ri. So, tau Ri is mi by 2 pi L Ri square. So, m for the first data point is 6.09 into 10 power minus 4 Newton meter, 2 pi is 3.14, L is 60 centimeter 60 mm. So, 60 into 10 power minus 3, Ri is 20.04 mm. So, 20.04 into 10 power minus 3 whole square. When you do simplification, it comes out to be 4.0245 pascals. Now, what you have to do? You have to generate all tau Ri values, these values similarly. Then what you have to do? You have to plot a curve ln omega versus ln tau. So, then this curve would be mostly a straight line. The slope of this curve would be used in the gamma dot Ri calculations or gamma dot calculations. So, gamma dot Ri is equals to 2 omega dln omega by dln tau r. So, dln omega by dln tau r from this picture, from this graph that has already been plotted here, we get it as 2.73. So, 2 into first data point of omega is 0.146 radians per second multiplied by the slope is 2.73. So, 0.7972 second inverse is the shear rate for the first data point. So, this is that value. So, similarly one has to construct all remaining corresponding shear rate information and tabulate them here, right. So, now this tau versus gamma dot, if you plot shear stress versus shear rate you plot, you can see this tau versus gamma dot curve, we can see that this fluid is showing some amount of tau naught, that is yield stress, and after crossing this yield stress we can see that it is showing a kind of shear thinning behavior. Shear thinning behavior with n is equals to 0.3661 and m is equals to 4.4166. So, and tau naught is given, this is Herschel bulkily fluid. So, tau naught h is approximately 3.5 pascals. So, this is how we can obtain the rheological behavior of a fluid using concentric cylinder rheometers. So, shear stress expression is same for all the cases, but shear rate expressions are different depending on the gap between the two concentric cylinders. One has to be careful in using these equations. Now, we will go to the other type of this rheometer, that is cone and plate rheometer. Cone and plate rheometer, this geometry seems to be first proposed by Mooney and Ewert, and then Russell has used this geometry for measuring the normal stress also. From this study only eventually the development of Weisenberg rigoniometer has been taken place, and then Ferranti-Sherley instrument was also developed based on this studies. Today the cone and plate viscometer with constant rate of shear rate and direct measurement of first normal stress by total thrust is probably the most popular rotational geometry for studying the non-Newtonian effects. However, now we are seeing only the corresponding equations for the shear stress versus shear rate information only. We are not going into the details of how to measure the N1 from the thrust, etc. But they are not too different. If you can simplify the equations of motion, different components of equations of motion, so then apply the boundary conditions accordingly. So, then you can get some expression about some information about the normal stress as well. So, now here we have a geometry here. So, there is a cone and there is a plate, and this is the plate of radius Ri, and then on this plate, like cavity kind of thing is there. So, then here what we have a kind of a cone arranged here. The cone angle is beta, that has to be very small, that has to be less than 0.1 radians for a proper geometry where the shear rate is independent of the distance or the space or in order to have a constant shear rate information, beta has to be very small. So, here this cone is rotating at angular velocity omega in a pi direction, and then theta direction is measured from the top here. So, from here to here this way. So, this is your theta is equals to 0 line, this is your theta is equals to pi line, this is your radial direction, right. So, now for this case what we have, we see that here the rotation is taking place in pi direction. So, then this is only v pi velocity is existing, and then this v pi is changing in the theta direction also because of the cone angle, and obviously it is changing in the radial position also because in the radial position the space is increasing as we go from the center to the edge of the cone. So, this we can see, whereas the other component Vr and then V theta are very small, that they can be negligible compared to the V pi values. And then general assumptions, we can have the steady laminar isothermal flow. Steady laminar conditions are mostly possible as long as the beta is small enough, and there is no body forces, beta has to be small. The whatever these liquid boundaries are forming at the edges, they are spherical in nature, and then symmetry in the pi direction, so that dou pi of anything is 0. So, when we apply these conditions in solving the r theta pi components, you may get some kind of information on the shear stress and the normal stress and then first normal stress components. So, one can solve those equations to get more details, but however we are not going into derivation of those things because they are irrelevant to the course, this particular course. We just need some kind of information about how to measure the tau versus gamma dot information from the rotation of a geometry. Now, boundary conditions, what we see at wall or periphery of the bottom plate is nothing but that is theta is equals to pi by 2. So, where that is the bottom plate is stationary, so V pi has to be 0. At cone lower edge, which is rotating with omega angular velocity, so lower edge of the cone is described in terms of theta as pi by 2 minus beta, pi by 2 minus beta, because theta we are measuring from the top, and this is at the lower edge. So, then V pi at theta is equals to pi by 2 minus beta is omega r sin pi by 2 minus beta, but sin pi by 2 minus beta is equals to cos beta, and then when beta is small, cos beta is equals to 1 minus beta square by 2 factorial plus beta power 4 by 4 factorial, etc. Higher terms can be neglected, and this is close to 1. So, what we can say at the lower edge, at the cone lower edge, the velocity V pi is equals to omega r. In order to get the shear stress information, after you simplify the pi component of equation of motion, we get final simplified expression, this one. What do you mean by after simplifying the pi component of equations? Let us say pi component of equation, there are terms like V pi, V theta and V r terms, tau r theta terms and tau pi r theta terms, and all those things are there. When we apply the assumption, the previous limitations that we have mentioned, so then most of the terms will be cancelled out, and then these are the only terms are remaining. We are not doing this derivation as of now, not required. So, after you integrate this equation, you will get tau theta pi is equals to C1 by sin square theta. So, now if you wanted to know the shear stress, you should know what is this C1. So, that you can measure by the experiments only. So, how do you measure by experiments? Let us say from torque balance on the plate, we get m is equals to integral 0 to 2 pi integral 0 to r square tau theta pi at theta is equals to pi by 2, that is at the bottom plate, dr d pi is equals to then when you integrate and apply the boundary conditions, you will get 2 pi r cube by 3 tau theta pi at pi by 2. In this equation, that equation number 4, if you substitute theta is equals to pi by 2, you will get tau theta pi at pi by 2 as equals to C1. So, you got this constant C1. Equation 4 will become tau theta pi is equals to C1, that is C1 is nothing but tau theta pi at pi by 2 divided by sin square theta. Now, also this information is incomplete, you cannot directly use, but from equation number 5, the torque balance, what we get? We get tau theta pi at pi by 2 is equals to 3m divided by 2 pi r cube, right. When you substitute here, so you get tau theta pi as function of theta, that is 3 m by 2 pi r cube sin square theta. But if your cone angle is very small, less than 0.1 radians, then we can have sin square theta is equals to pi by 2 minus beta is approximately close to 1. So, then tau theta pi is equals to 3 m by 2 pi r cube. So, this is the expression that you can use to obtain the shear stress information of the particular fluid. If you know the torque, now we have to see shear rate information, how to get shear rate information from the angular velocity. So, tau theta pi is nearly constant that we have seen the previous expression. This tau theta pi is 3 m by 2 pi r cube. For a fixed rotation, the m is fixed, so then this is fixed actually. So, that means it is almost constant for this geometry. So, if it is constant, it is also possible that shear strain and shear rate would also be constant. So, shear strain we can get as gamma is equals to d phi by d theta, that is phi by beta, because it is because of small angle and small displacement. And then from rate of deformation tensor, we have this gamma dot is equals to sin theta by r dou by dou theta v pi by sin theta. This is from the rate of deformation information that we can get from any books in spherical coordinates. Okay. Now, if you rearrange this equation, it would be differentiate and simplify this one, we will get 1 by r dou v phi by dou theta minus v phi by r cot theta. Because now in this case theta is pi by 2 minus beta. So, because that is lower edge, the angle is beta. So, that in terms of theta, if you write, that is pi by 2 minus beta. So, under such conditions, cot theta is equals to cot pi by 2 minus beta is equals to tan beta. So, for small beta, tan beta can be approximated as beta plus beta cube by 3 and so on. So, this higher power terms can be removed. So, under these constraints, the velocity profile would be omega r pi by 2 minus theta by beta, which is a very good approximation. We can derive and then prove this one also, but not necessary as of now. So, then now you make use of this v phi information in this expression, gamma dot is equals to 1 by r dou v phi by dou theta minus v phi by r cot theta, and then simplify, you will get gamma dot is equals to or approximately equals to omega by beta. So, using this information, one can obtain the shear rate information from the angular velocity of the rotating part of that particular geometry in a cone and plate viscometer. So, now what we do, we see example problem and then see how we can get the shear stress versus shear rate information or rheological behavior of a fluid using this cone and plate rheometer. So, example problem, a 25 mm radius cone plate system with beta given this value is used to obtain the following steady shear data for a food product at 295 Kelvin. So, the angular rotational velocity is given for the rotating cone, and then the corresponding torque is given. From this information, you are supposed to get the tau versus gamma dot information. So, tau you can get 3 m by 2 pi r cube, and then gamma dot you can get omega by beta. You can apply these principles and then do the simplification. So, let us take the first data point. Omega is 2 into 10 power minus 3 radians per second, m is equals to 1.34 into 10 power minus 4 Newton meter. So, cone angle is this one. When you convert this cone angle in radians, you will get approximately 0.02 radians, which is much less than the 0.1 radians that is required in order to use this tau theta pi and then gamma dot in equation. So, we can safely use them. So, tau theta pi is 3 m by 2 pi r cube, m is 1.34 into 10 power minus 4 first data point, and then r is 25 mm. So, when you simplify, you will get 4.1 pascals. Similarly, gamma dot is equals to omega divided by beta. First data point of omega is 2 into 10 power minus 3, beta in radians is 0.02. So, you get 0.1 second inverse. So, first data point shear rate is 0.1 second inverse, and then shear stress is 4.1 pascals. Similarly, you can construct this tau versus gamma dot information and then fill the table like this. So, you have the tau versus gamma dot information, you plot, then you can get the information about those the rheological behavior of this particular fluid. So, when we plot the shear stress versus shear rate, what we see here also, this fluid is showing some amount of tau naught. After crossing this yield stress, it is showing a kind of shear thinning behavior with n is equals to 0.2974 and m is equals to 7.6364 Pascal second power n, and then tau naught h is equals to approximately 4 or 3.5 Pascal, something like that. So, since after crossing yield state is showing nonlinear behavior, it obeys Herschel-Berkeley nature. So, it can be said as this particular fluid is a Herschel-Berkeley fluid. So, next possible geometry in the rotational viscometer is parallel disc rheometer. This geometry was suggested by Mooney. It consists of a disc rotating inside a cylindrical cavity. It is extensively used in rubber industry. Russell has also used this geometry for measuring the normal forces. Greensmith and Rivlin measured pressure distribution using this geometry. Koeta et al. Used this particular geometry to obtain the normal stresses. The geometry as well as the flow behavior is more or less similar to the cone and plate geometry, and most instruments under this geometry permit the use of either geometries, like most of the commercial geometries permit either of the geometries like cone and plate and parallel disc rheometer in one particular set itself. However, in contrast to cone and plate rheometer, flow between parallel disc is not homogeneous. So, in such case we have the schematic is shown here. So, here we have a disc inside a cylindric cavity, and then this disc is rotating at angular velocity omega. The radius of this fluid boundary whatever is there, that you can take, or the radius of the disc, the radius of the disc is capital R, and then this is your R direction and this is your Z direction. This in the theta direction it is rotating. The confinement area that is available, height of the confinement area is h. Now, here also we have to do similar analysis to get the expression for the shear stress and shear rate equations. So, how to do that one? So, in these conditions, if the gap this h is small, then one can have a steady laminar flow, and then we see that it is rotating in the theta direction. So, v theta velocity would be there, and then the Vr and then v theta is existing, and then Vr and Vz are small, that one can neglect them, negligible, and negligible body forces. This whatever cylindrical the fluid edges they are forming, they are cylindrical in nature. So, one can use the cylindrical coordinate system for this particular geometry. So, with one disc stationary and other rotating at omega, assuming no slip at either surfaces and neglecting inertial forces, the velocity must obey this particular thing, because under such conditions if you are neglecting inertial forces, the velocity profile would be a kind of linear profile like as shown here, that is r omega z by h. So, the corresponding shear rate expression is r omega by h. Similarly, strain goes from 0 at the center to a maximum at the edge. So, then we have gamma is theta r by h. So, we have the expression for the shear rate, we have the expression for the shear strain. Now, in order to get the shear stress expression, we have to do torque balance. So, torque balanced by the shear force, m is equals to 2 pi integral r tau theta z r dr. This tau theta z is function of r only. Now, what we do using this equation 1, you can write this r is, we are actually changing the variables from r dr to, we are trying to write d gamma dot something like that, changing variables. So, from equation 1, gamma dot r is equals to r omega by h, we can write r is equals to h by omega gamma dot. Now, at r is equals to capital R, gamma dot r would be omega capital R by h, omega capital R by h, that is at the edge of the plate disk, whatever we have considered, right. So, from here h by omega we can have this h by omega is equals to r by gamma dot r. So, now this h by omega you substitute here as r by gamma dot r. So, then what we have, r is equals to capital R gamma dot by gamma dot at r is equals to r capital R. So, similarly dr would be dr is equals to r by gamma dot r, because r and this gamma dot capital R are the constants, whereas this is changing with radial position. So, this is d gamma dot. So, now you make use of this r, substitute this r and dr values expressions in equation 3. So, then you will get altogether a new expression here like this. When you substitute r and dr in this equation number 3, we get m is equals to 2 pi integral 0 to r by gamma dot r whole cube gamma dot square tau theta z d gamma dot. Now, you rearrange this equation, that means like you take this r cube and 2 pi the other side in the left hand side. So, what you have this m gamma dot r cube by 2 pi r cube is equals to integral gamma dot square tau theta z d gamma. Now, this equation you differentiate either side by gamma dot capital R, that is gamma dot at r is equals to capital R. So, then we have this thing. So, from this equation what we have in the right hand side, you can apply the Leibniz rule. After applying the Leibniz rule and then do the simplification, you get an expression for tau theta z as function of r is equals to m by 2 pi r cube multiplied by 3 plus d ln m by d ln gamma dot r. From this information one can get the expression for the shear stress. So, we have the expression for both shear rate and shear stress. If the fluid that we are testing is obeying Newtonian fluid, then what we get? We get this d ln m divided by d ln gamma dot r is equals to 1. So, accordingly tau theta z would be 2 m by pi r cube. So, in general this apparent this apparent shear stress given by equation number 6 is often used to calculate the apparent viscosity, because for this case you need to know only one single torque measurement. Now, we see some kind of advantages of this particular geometry compared to the other geometries. So, in this parallel disk geometry, loading and unloading of viscous and soft solid samples is much easier compared to the other rotational viscometers. Parallel discs are usually preferred for measuring the viscoelastic material functions. It is also very useful for obtaining viscosity and then normal stress data at high shear rates. So, equation number 1 can be used to get the high shear rate either by increasing the rotational velocity or by decreasing the gap. So, under those high shear rates also this can be used. So, errors like secondary flows, edge effects, shear heating etc. may be reduced by small gaps. Another use of data collected at different gaps is that using the different data at different gaps one can obtain the wall slip effects in the parallel disk rheometers. Now, we see an example problem here. So, following rotational speed torque data has been obtained for a 3% aqueous polymer solution at room temperature and pressure using a parallel disk rheometer with H value 0.7 mm and R value 25 mm. So, the rotational angular velocity is given and then torque is given. From here, from this information we have to get tau versus gamma dot information. So, how to do? We have to use the equation just now we have developed. For the first data point, let us do the calculations. Gamma dot at capital R, now we are at the edges we are seeing it. So, at R is equals to capital R, gamma dot is equals to R by H omega. So, then R is 25 mm, H is 0.7 mm and then omega first data point is 3.56 into 10 power minus 4 radians per second. When you simplify this one, you get gamma dot as 0.0127 second inverse. Tau is equals to m by 2 pi r cube multiplied by 3 plus d ln m divided by d ln omega. So, when you substitute m and omega values, r value here and then simplify, you will get this 0.454 pascals, because this d ln m by d ln omega is the slope of the curve ln m versus ln q. This d ln m by d ln omega value 0.842 is the slope of ln m versus ln omega curve. So, that is shown here, that is giving a straight line. So, from this straight line the slope you get, the slope is 0.842. Corresponding shear stress value for the first data point is 0.454 Pascal. Similarly, other cases also you can get the shear stress versus shear rate information, this tau versus gamma dot. This tau versus gamma dot shear stress versus shear rate information, they obtain converted information, that is obtained information from m versus omega, you can plot. So, then you can see this gives a kind of passing through a origin. So, it is not having any yield stress as in the two previous example problems, and it is showing a kind of shear thinning behavior, weakly shear thinning behavior with n is equals to 0.8889 and m is equals to 28.025 Pascal second power n. So, it is a shear thinning fluid. So, this is how using rotational viscometers one can get the shear stress versus shear rate information. One can also get the normal stress information, but we are not into those additional details of normal stresses at all, because we are not interested in the viscoelastic fluids in this course. Finally, it is to mention here, like in the capillary viscometers also, here also there is a possibility of sources of errors like end effects, wall slip, secondary flows, etc. are possible in all of these rheometers. There are also possible corrections for them also, but however we are not going into those details as they are not important for this particular course. The information provided in this lecture are mostly taken from these two references, rheology by Macasco, non-Newtonian flow and applied rheology by Chabra and Richardson. Thank you.